the low temperature properties is one of the important properties of rubber, and it's a property which have been more and more important, especially as say in the automotive industry, the manufacturers, they want to make cars or trucks or whatever, which would be possible to use all over the world and not only in, let's say, their own climate. And that's why it's many times difficult to reach, say, down to -40 and still have a good function. If the polymer at the same time should maybe work at 200 Celsius sometimes, or a very high temperature. So if we look, the rubber is very dependent of the temperature. The modulus or stiffness. Here is a chart of an say dynamic mechanical test where we have the stiffness or E modulus on this axis, and we have the temperature on the other axis. And many polymer materials can have two transition points. All polymers have a glass transition point, which is in fact the mid of a range of a, where if you measure it dynamically, you have the maximum of the damping in the middle of that range, and that you take as the glass transition temperature. Then you can measure the glass transition temperature in other ways with a DSC, and then you won't get exactly the same temperature. It will be a difference. But anyway, some polymers also have a second one, and that are polymers who maybe have a tendency to crystallize.
Well,
yeah, someone. And for rubber, we don't have so many polymers where we have this effect, but we have some of them, chloroprene, for example. And in fact, this is not a rubber tested here, it's a polyethylene, because polyethylene gives a very good example of the two transition points. We have the glass transition, which below that, the material is very stiff and brittle. You can break it very easily. And then you have the materials which crystallize. The crystals, they melt at another temperature. For polyethylene, for example, around 120 Celsius, where the TG for polyethylene is something like -100 Celsius. Here we have a similar test made on an actual rubber, an EPDM. And we see one interesting thing, that we only have one transition here. There can be on some EPDMs, it may be a little crystallization if you have, say, a low content of propylene. But anyway, we see the big difference in more normal temperatures. Up here is +50 Celsius, and we go down to 0, a little below 0. There are enormous difference in the stiffness of the rubber, depending on the temperature. As we see that it's a logarithmic time scale. So it means that even within, say, the normal temperature range of rubber in a laboratory, that is 23 ±2 Celsius, it's even there quite a big difference in let's say, hardness, which I measured once, the hardness just within a 4 Celsius degree range. And that is something like half a degree in hardness, at least. So it's very important, the temperature. If we look at the standardized test methods for rubber, we have brittleness point. We will go through them in more detail later on. We have low temperature compression set. We have the low temperature stiffening or Gehman test, the temperature retraction, TR test. We can measure increase in hardness. I will not discuss that so much. A similar test is determination of crystallization, where you leave the material a little longer time at low temperature, and you can see the increase in hardness due to crystallization and not only to temperature. And then we have methods for dynamic mechanical analysis, which produces curves like we saw before. The brittleness point is the lowest temperature at which a rubber does not break when you heat it. And if we look in the standard, it looks like this, the drawings. You have a hammer, it can, and you have the samples, which are attached to a specimen holder, and you hit them, and you have a lot of distances and measurements, which are important. And the stroke can be either vertical, or it can be and rotating. And the speed should be 2 meters per second. And then they're also required a certain impact energy so that the speed does not say reduce more than 10% after the stroke. Here is a picture of an older instrument. I don't know if it's made anymore. I don't think so. It was made by TR10 in Italy. It has a rotating function. It's a motor running all the time, and a bath with ethanol in, and you cool it by liquid nitrogen. And then when you do the test, you start at a temperature which is so low, so you expect the material to break. And if the material breaks, then you put in new samples, you cool them down, condition them, and you hit them again. And normally you go up in 2 Celsius degrees steps until you get the temperature where it doesn't break, and that is called the brittleness temperature. The motor in this instrument is running all the time, and it's a clutch then attached to the stroking, the hammer, which makes the stroke only goes 1 revolution when you press a button. I've been involved in improving that standard, and some years ago, it's several years ago, in fact, we decreased the tolerances. We had a better specification of the clamping device. It was introduced a new method B by Japan, by the way. If you say have 6 test pieces, which is suggested, and they don't break all of them, then you go up in temperature to next level, and then you can get some kind of interpolation between the 2 temperatures. And we also have nowadays precision data included. Here is what we consider a more modern instrument. It's computerized. The instrument for impact test is the test rig in the front. This is an instrument where you can attach different low temperature instruments in the same, and you can change the method by a carousel. But what we see in the front is a brittleness tester with a vertical hammer, and the speed is depending on the falling height. So it can be adjusted so you get the right. And the speed is then also measured after the impact to see that it's not reduced. And you can add weights to get the sufficient energy in the stroke which is needed. In this picture is a little wrong. It's only 1 weight to test. It should be 4 or 5 weights normally. A report can look like this, especially if we then do the so-called 50% evaluation. So we have at different points. So the computer doesn't make too much calculations here, in fact. Another test which had been specified in some specification, that is the low temperature compression set, which I call LTCS. And this is like a normal compression set test, but you do it in low temperature, and you measure another property. You measure how it will recover at low temperature. And the sample is compressed, put in a low temperature environment for 24 or 72 hours, compressed to 75% of original height. Then you release the compression and you measure the recovery, say after 30 seconds and 30 minutes, that's 1800 seconds, and sometimes also 2 hours. Originally, this test was done that you had some kind of compression device where you could easily remove the sample very quickly. Because if you should be able to measure 30 seconds, you need to be quite quick. And in the traditional way, you put this test rig, or several of them, in a freezer. You put in a thickness gauge, and then you open the lid to the freezer, put your hands on the head down, and try to measure this within 30 seconds. And that's not easy. Some with more financial muscles, they maybe have bought a glove box, means a temperature box where you could have your arms put into gloves, and you don't need to expose the sample so much for the environment. But still, when we made an in-laboratory test comparison in ISO many years ago, we found that with 95% probability, people had, the laboratories were more than 100% apart. So you couldn't get more or less whatever you liked. You didn't get any reliable results. Unless you had maybe a glove box would help improve the whole thing. As soon as you touch the sample, and if you don't keep the time of 30 seconds, you will get different results. 12 years ago, we changed the standard. We looked at tolerances. We introduced a new compression assembly, which makes it possible to do the test, say, do the maneuvering of the test fixture from the outside and don't open the freezer. And that improves the repeatability and reproducibility quite a lot. Here is an example. It looks a little like a stress relaxation rig, and it's based on the same. But here we have the test piece in the bottom. We have some insulation and leads. So we have this sticking up, and the rest is standing on an aluminum plate in the freezer. So we get the temperature transferred from the aluminum plate to the test setup here. We measure temperature very close to the sample. And then we apply a weight which is resting. Yeah. We compress it first, and we can use spacers as in a normal compression set rig. And then when we have it 1 day or 3 days in the low temperature, we release, say we turn this about 2 millimeter at two revolutions. And then we only have the upper compression platen and this bar resting on the test piece. And the weight of this is calculated so it will give the 23 kilopascal you have when you measure thickness on rubber. To make that possible, the rod here is made of titanium, unless it was too heavy if we used steel. This will be a little different results compared to if you do it in the old-fashioned way, where you didn't have the measuring force on the sample the whole time. But it gives enormous much better reproducibility and repeatability. And with this system, it's also possible to do it in the old way of just measuring after 30 seconds or 30 minutes and or. Because you can raise it so much so it doesn't rest on the sample, and then you move it down to measure the sample thickness after 30 seconds and again after 30 minutes. But then then this is connected to a computer and a software. So we record the millimeters, and we control and record the temperature. And the result curve can look like this. Here are 3 different materials tested. See if I could remember what materials we had. The first is the fluororubber. See it very, and that is the red one. a nitrile rubber, the blue one, and the green one is a natural rubber. We can see the time scale is here is 2 hours. And the natural rubber recovers very quickly. Sorry. The nitrile rubber is not so quick, and the fluoro rubber is not so quick either. And the natural rubber doesn't change so much over 2 hours, but we get more change over 2 hours from the other two polymers. And then the software will calculate the recovery or the compression set after the times you want, for example, 30 seconds, 30 minutes, 2 hours, which will be printed in the test report later on. If we then look at the ISO 1432, the low temperature stiffening Gehman, it's I think a quite interesting low temperature test because it measures the stiffness modulus, and often you only measure the relative stiffness. So first you measure the stiffness at room temperature and then the stiffness at different low temperatures. If you know the size of the test piece, you can also calculate the modulus in the torsional modulus in megapascal. The principle of the Gehman test is that you have a test rig. You fix your sample here, that is down in the ethanol box to get the low temperature. You have a rod which is connected to a calibrated steel wire, spring wire, which have a known stiffness or known modulus. Then when you measure, you turn all of these 180 degrees, then the twist will be divided between the calibrated spring wire and the rubber. And if you then know the angle between, this is an angle transducer, then you can calculate the stiffness of the rubber, as you know the stiffness of the steel wire. And we get quite good, say, accuracy measuring the angle shift here. The important thing here is to don't have any friction. That's why the instrument we offer have an air bushing here, so you have an air without friction. If you look at the traditional instrument made by Wallace in England, I think that's the one the original standards was written around, because it even described how you should do in detail handle the instrument. That is now changed in the standard to a more general description of the principle and not describing a single instrument. But in this case, you have a bath with ethanol, you have the heating element, you have a stirrer, and you increase temperature manually by increasing this thermostat here. In this case, you had up to 10 samples, position here, and you move the measuring head. Here is the torsion wire up here, and there was a needle showing the angle on this scale. So it was not possible to measure more accurate than 1 degree, maybe, degree in angle. And as I said before, it was originally describing the Wallace instrument, but now it's more a general standard, including all the other instruments like automatic ones. And here is the one we can offer. 6 test stations. You can test 2 series of materials at the same time, or even 3 if you don't only want to do double tests and not triple tests. And also here we cool it with liquid nitrogen. But one thing we often recommend is that you also have a low temperature freezer, say a freezer down to -85, and then you can pre-cool the liquid, the ethanol, because then you don't need to use so much liquid nitrogen. And if you're running just a single test one day, you don't need the nitrogen at all. You can just use the pre-cold ethanol. But you have to fill the bath twice. First one time, take it out, and then another time to get down to minus 75 or 73. The result can look like this. Here we have been running double tests because we don't get very much variation between the test pieces. The red-blue curve, the first one, it doesn't say what polymer, but I'm sure it's natural rubber because it's normally in the range here. And then there are two other polymers. And you can set what evaluation points you like here. RM stands for relative modulus. That means relative to room temperature, because you start the measurement, measure the stiffness at room temperature, lower it into the bath, wait 10 minutes, and then you start to go up 1 degree per minute, and you do the stiffness measurement at regular intervals, say every 30 seconds or every 60 seconds. And then we start to record the values from 100 times stiffer. Here is, in fact, it's not a usable material. Normally in the specification, you maybe want to say 10 times the stiffness at room temperature is something where you still can use it as a rubber. But the interesting thing, you also get, say, the slope of the curve. These two are much steeper, and the one here for natural rubber. So you can get quite a lot of information from this kind of test. The next test, which is very popular in many places, it's the temperature retraction. And there a test piece, it's stretched at room temperature and then cooled to a sufficiently low temperature. And that is normally recommended minus 73 in that area. Then most polymers will not, well, you stretch them and then you lock them in place, cool them down for 10 minutes, release the locking. And then most polymers, except for silicone, it will still be elastic at that temperature. And then you start heating 1 degree per minute, and you measure the recovery in length. Here is the illustration from the standard. It's a principle. It's in fact of an instrument made in Sweden, by the way, a long time ago. We still have it in the standard. I was project leader once for updating the standard, but I kept the illustration because it's quite tricky to make new illustrations. And the important thing is shown. You have a test rack where you can stretch and lock your samples. You have a locking nuts here. You have a heater of some kind. You have a propeller to agitate. So the principle are still okay. Here are pictures of it. The one we see here is one I have in my museum. I collect some old rubber testing instruments as well as some other old or sometimes not very old things, but not modern, like telephones. It's popular. They get the old-fashioned very, very fast. But this one, I've been using that when I worked in a rubber company in Sweden. There we measured on a graduated scale, and we have a thermometer and a heater, and we had to sit there for a couple of hours to look at the very slow recovery of the material. One thing I always wonder, by the way, is why we have 4 test pieces here, and the standard recommends triple test pieces. I don't know why. The man who designed this, he died not too far, so I think last year or this year, so I can't ask him anymore. The other one we see is a TR tester from Chias in Italy. I don't think they make it anymore. And in Modulus in England have had a similar one, around one with 6 test pieces. But it's the same principle. You can lock it and you can measure on the scale. What we have done a couple of times in the ISO standard, we have stricter tolerances because we get quite big variations in results when you just measure the, say with 1 millimeter accuracy. Now we can measure with more like 500 millimeter. And with more automatic control, computer control of temperature rise and everything, we get everything more accurate. Here is the also 6 test piece test rig, which is lowered into an ethanol bath. By the way, we had customer in US once who wanted to have silicone oil in the bath. We had to make some modifications to allow that, and then we sent the instrument to the customer in US, and they complained after of the year that it's leaking. It's leaking. We get silicone oil below the instrument. So we even had the service guy going there and replacing the whole container for the liquid. And we got it back and we investigated it, and it was no leakage. But if you use a silicone oil at low temperature, it has to be enormous low viscosity. And silicone has a tendency to creep upwards. So it creeps up along the walls, over the edge, and then down on the outer side of the container and comes out below the instrument. So I don't recommend silicone. Even if it's good for one reason, it doesn't burn. The results from the TR test could look like this. Still, we use only 2 samples per material. And the first one here is still natural rubber, I suppose. The other 2 I can't guess. Yeah, we have one fluororubber. Because that goes over 0 Celsius, you see, to get to recover to 70%. And here we then have the normal, but we take 10% recovery, 30%, 50 or 70. And we also included one thing here, the difference between 70 and 10%. It indicates, say, how steep the curve is here. Because you can see that the fluororubber starts quite low temperature to recover, but it goes very slow. And some other materials, they go much faster. That is also interesting. And that you will get when you have it on a graph like this. And then we combine all of these 3 methods into one instrument. And it's a little heavy piece, by the way. But it was quite good. It's easy to change between the test methods. You just swing it around, and the sensor knows that you have another method. And you have to change the type of test in the software as well. By the way, to use liquid nitrogen, we have the liquid nitrogen container here. Then we use a type with so-called self-pressurizing. It means that normally the evaporation of liquid nitrogen gives a little pressure inside, but if you need to have more flow of liquid nitrogen, you need to add to that pressure, and that is then a little coil here. So you will take up some liquid nitrogen in that coil, it evaporates and goes down the back as a, say, pushing gas, pushes out to keep the pressure of around something around 1 bar. So you can use other way of cooling. One way is to use carbon dioxide ice. That goes down to -75 roughly, so it's a quite good temperature. And in the old times, you put that directly in the bath. But then you may get different temperatures in the bath, because often you had some carbon dioxide ice in the bottom, and then you get transients from the bottom to the top in temperature, and that was not good. To avoid these different temperatures from top to bottom, we have the agitator we have in the bath is like a pump. It pumps from the bottom to the top, so we have circulation in both up and down and sideways, because it's important to have the correct temperature. And also then the temperature sensor should sit quite close to the samples, so you really measure the temperature close where the samples are situated. Then you can get very good repeatability and reproducibility. So summary, totally here, the results and experience we have with automated low temperature testers shows a much improved accuracy together with a good reduction operator time. I may tell you something. One of my customers in North America, they bought one of our automatic TR tests. It might be 20, 25 years ago. And they had one man doing TR test the whole day. Another man in the lab was doing the Gehman test the whole day. And they were so impressed by the TR test because now the man only needed maybe a quarter of a day labor to put in new samples and so on. And you could do something else. And they could maybe produce 50% more tests as well, because he could start the test before going home. And that could finish automatically. And when he came in the morning, the instrument was already cool and ready to run the next test. So he asked us to, could you develop Gehman tester as well? And that was more tricky. But we made one. They even placed an order for 2 Gehman testers before we even had the drawing. And 9 months later, they got the first Gehman tester, and some months later, they got the second one. And they could motivate that with that they saved money because the operator were not busy all the day. But it's very few times you can have that as a motivation for say an automatic instrument. I have one more thing I want to show. I have to collect that from my hard drive. Some years ago, we made an comparison between different low temperature testing methods to see, say, how we didn't have Brittleness, but we have Gehman TR test and low temperature compression set and DSE and DMA measurements. That could be interesting to show in connection with this. So I will try to get that, pick up that from my server. Sorry, I have to go there. Do you see this report now?
Yes, we see it.
You see it? Very good. We had 2 compounds, EPDM and nitrile rubber. We tested Brittleness. I forgot that. Low temperature compression set, Gehman, TR, TG by DMA, TD by DSE. And we have a little table here. It's possible to read. We have Brittleness. It seemed to be close to the TD measured by DMA. By DSE, we was a little more different. Well, it depends on the polymer as well. So we know that Brittleness is quite close to the glass transition point. The compression set at low temperature, I don't know we can correlate that at all, by the way. But if we look at the Gehman test, ISO 1432, then the 50